Hello and most welcome to an speech and questioning round with Professor Petter Mostad of Chalmers University. Most welcome, Petter.
Thank you.
We are having you once more, and we are extremely grateful for that. And you were especially looking for participants that I can almost promise that we'll have at least two the next time. We'll make a more proper lecture of it.
Mm-hmm. Yes, I'm very happy, of course, that a subject like statistics, which very rarely generates much enthusiasm among audiences, now seems to be something that people want more of. So, of course, that excites me. And I thought that this time I would actually prepare a little bit better and talk a little bit more on actual Bayesian statistics, and still from a philosophical point of view, but a little bit also about the technicalities of it, so that we all understand and know that.
Fantastic. So I leave the word to you, Petter.
Okay.
Please go ahead.
Okay, thank you. Yes, so let me see if I let me see. Yes, let's start here. So let me see, maybe I can we do like this? So okay, so this is, as I said, a bit on Bayesian statistics from a philosophical point of view. And so what kind of philosophical starting point could you have? Well, one possibility is to say that we ask the question how to interact with the world and act in a beneficial and logical manner. This is a very basic question that all thinking entities will face. How can we actually act and interact with the world in order to achieve whatever we feel or we have as a goal somehow? And I would argue that in order to do so, what we do in practice is to make models. So we make a model of some part of the world, which is a sort of a mental map of a part of the world, so that we can, that's what we mean by saying that we understand that part of the world. So, you know, the baby that screams to get fed will have sort of a model of the what happens when you scream. Well, you get food most of the time, at least, or sometimes. You know, if you want to travel somewhere, you can make a map, or if you want to understand your surroundings, you make a map of that surroundings, and that can be a mental map and sort of, in that sense, be a model of those surroundings, and you have all kinds of models like that. Now, the purpose of these models, I would argue, is to predict, and to predict consequences of actions. So in the view of, I mean, starting with the first goal here, to you know, how do you interact with the world to have some good consequences? Well, you want to predict the consequences of those actions that you have. So, and when the models are tools for that, then the predictions of the models are what is central. A model that cannot make a prediction is not really useful as a model, and I would argue shouldn't really be called a model at all. So in that sense, for example, a map is a prediction of what happens if you go somewhere. You will see this thing, or yeah, you can imagine all kinds of other things that can be framed in terms of predictions. Okay, so what kind of models are there? Well, the simplest type of model, or is a deterministic model, which says that, you know, for example, if I do this, then this will happen. Or, yeah, it's simply a set of rules saying, you know, connections between different things that you may observe. If you observe this, then this will also be observed afterwards. However, the models that we actually use and make from an earlier age, well, they are very simplified models, and they are very rarely deterministic, or it's very rarely sensible to make deterministic models because they are very much simplifications. So it means that what will happen is, well, sometimes this will happen, sometimes not, and sometimes, you know, more often it will happen in this case than in that case, and so on. So that leads to what I think is you know, formally called a probabilistic model, or you know, it can also be in the mind of a child, for example, or a developing intelligence. It can be less formalistic than that, but in the formal sense, it means that the different outcomes, the different states that the world could be in this simplified model, are assigned a number, a positive number, and the sum of all those numbers for all the possible states that the world could be in should be equal to 1. So, and we call those numbers probabilities for the different states. Yeah, so this is, you know this very well. I mean, you have a model, for example, for the weather tomorrow. You say that the probability of rain is, well, here in Gothenburg, it will be like 90% chance of rain tomorrow, and then maybe 1% chance of sun, and then 9% chance of cloudy, and then that sums to 100% or 1, and that will be a probabilistic model for the weather tomorrow. Now, there is a philosophical question here, because what do we mean by these numbers? So what is the interpretation of the probabilities in a probabilistic model? For example, in this weather forecast model for tomorrow, before tomorrow, we only have these probabilities, and then tomorrow occurs, and then there will be some weather. And that weather will, I mean, tomorrow will only come once. So you don't have a repeated occurrence of tomorrows to count the frequency with which there will be rain and the frequency with which it will be sunny, and so on. So what do we then actually mean by saying that something has a certain probability in a probabilistic model of this type? It's not easy to make a very precise statement about that, but I would say something in the direction of putting this on a more general level and saying that, you know, in general, things that we assign a probability 0.3 or a probability 30%, well, in 30% of cases of those types of events, they should occur, even though it's different events with you know, different models and different predictions. You know, on average, that should happen for those events, but it's not the same event that can be repeated in many ways. But there are, at least for me, there are some unclarity about exactly how to define the probability, what we mean by saying that a certain thing has a certain probability in a model of this kind. Okay, so what I thought now was that we should make we should carry this over to Bayesian statistics, and in order to do that, we make an example, a very basic example. It's a hidden disease, and it's a way to compute with these probabilities. And to me, it's very important that you understand what it means to actually a little bit of how to do these computations, because that's necessary to also understand the philosophical consequences of this. Okay, so this example, and now we can just forget about the philosophy and just do a very practical thinking. Indeed. So there is some kind of hidden disease. So in other words, there's a disease that people can have without knowing directly if they have it or not. Maybe the consequences of the symptoms will come later or whatever. It's sort of hidden, but we know that 1% of the population has this disease. Now, because it's a hidden disease, you want to test for it, and a test exists, but it's very unreliable. So the test for the disease gives a positive result for 90% of those that have the disease. So even if you have the disease, it's not certain that this test will be positive. And also, and maybe even worse, is that even if you don't have the disease, there's a 10% chance that the test will still be positive. So you have an imperfect test with these probabilities in each of the cases. Now, let's say that you wonder if you have this disease, you go and take a test and you get a positive answer. Now, what is the probability that you actually have the disease? If you want to make predictions of your future life or whatever, then you want to know what is the probability of actually having this disease. How can you compute that? And it turns out that this is easy to do using Bayesian statistics. So let's do that. Now, the first thing we do then is to make a kind of model for the world. Like we said, a probabilistic model for the world. And in this model, it's basically 4 different states of the world that are interesting. So let's say that it's one of these 4 squares that represent each of those 4 states. And one here is that you are sick, or you have the disease, and that the test will turn out to be negative. There is also the possibility that you are sick and that the test will turn out to be positive. It's also the possibility that you are healthy and that the test is negative. And finally, that you are healthy and that the test is positive. So this divides the possible states of the world into 4 states. So it's kind of a simplification of everything, but it's exactly the simplification we need in order to do this particular computation. So this is then the state space. And how do we now assign probabilities to those 4 values? Well, it turns out that it's possible with the information that we have, because we know that the 2 states on the left, they represent...
Sorry, Petter, there's nothing showing on the screen here.
Okay, so then we need to, let me see, stop share, and then let me see, let me see, share screen, and then Okay. So now, can you see something happening?
Yes, there's a square coming up.
Okay, good. So now, I'm sorry, I'm a bit rusty in the technical things here. So,
No worries.
but thank you for stopping me there. So, so we have four situations. It's let me write it again: sick, negative. It's sick, positive. It's healthy, negative. And it's healthy, positive. Okay, and now we want to assign probabilities to these four states. Now we know that the two states on the left represent the situation that a person is actually sick, has the disease. Now we know, or we are told in this exercise, that the probability for that, for a person being sick, is 1%, because 1% of the population is sick. So that means that the sum here is equal to 0.01, or 1%. And the sum here is equal to 0.99. So now we have some idea of this thing. And then if we look at the two states on the left, then we know that if a person is sick, then the probability of getting a positive test was 90%.
Yeah.
So that means that the probability here will be 0.01 times 0.9. And the probability here will be 0.01 times 0.1, 10% of the cases. So we subdivide that probability of 0.01 into those two, so that they have the same ratio as this test indicates that they should have. So this is then 0.001, and this is 0.009. Okay, so we have probabilities for those two states. On the right, we can do something similar. Here, 0.99 and 0.99. We have to multiply that with the probability that here that a healthy person has a, well, down here, that the healthy person has a positive test. That was 10%. This is 0.1. So this is now 0.099, and this, the probability that the test is negative for a healthy person is 90%. So this is now 0.891.
Oh.
So now we have assigned four numbers to these four states, and these four numbers will sum to 1. And they represent our model of the real world as pertains to this particular question that we want to answer. So that's the first step of sort of describing a model. And notice that we describe the model before we have actually observed anything, before we have observed that this person or me that we are talking about has a positive test. So we look at the world before we have observed data.
Could we call this a prior?
Yes. So this is the prior in some sense. Yes, it's the prior is used sometimes in a more technical sense of only the parameter part of this model, but even more general sense, you could say that this is the prior model.
Ah, okay.
Okay. So now what happens is that, well, there is a positive test. This means that it's only these two states that are actually possible. The other two states are no longer possible. So what happens in Bayesian statistics is that you simply discard those states that are inconsistent with observations. This is the basic and very central idea of Bayesian statistics, and it's really the only idea of Bayesian statistics, that you discard the states which are inconsistent with observations. So let's do that. Let's see if I can do it here. I simply remove, well, now it's removing a lot here, but let's say that we no.
Oh no.
Let me see. Draw. Yes. So now we have these two states left. Okay. So this is now our new model. However, the probabilities no longer sum to 1. So what we do is that we have to rectify that by adjusting the probabilities so that they sum to 1. This is also the sort of the technical part of Bayesian statistics, that you adjust these probabilities. So what is the sum here? It's 0.009 plus 0.099. So that has a sum of 0.108. So now we adjust these. We divide them by the same number so that they sum to 1, but have the same proportion. So basically, the updated probability here is 0.009 divided by 0.108, which is equal to 0.08333. And here it's 0.108 divided by 0.099 divided by 0.108. So this number here divided by that number, and this is 0.91666. And that's it. So now the final step is to use this for prediction. So I'm saying that I have a positive test. What is the probability that I'm actually sick? It's this number here. It's 8%. So this, maybe it also illustrates a little bit the utility of this, because maybe it's surprising for some people that even if you have a positive test, then it's only 8% chance that you are sick in this case.
Yeah, it's a surprise, definitely.
Yes, and the reason for this surprise, if you think about it, is that this is a lousy test. You know, basically that before you have taken any test, it's overwhelmingly likely that you are in fact healthy. And then when you have a positive test, well, the explanation for that test is probably that this is a false positive, because you're probably healthy anyway. So this is like probably a false positive, but it of course could be a true positive, in which case you are sick. And the probability of the last thing is 8.3%.
Wow, that's a surprise and a half.
Yes, but if you think about the situation very carefully, then you will see that this is true. And of course you can do the same thing with lots of other examples, and you will find that you will be able to make similar computations. Some results will be surprising and some will not. Let's see if I can now go back to the presentation. So now you see the presentation again, I hope.
Yes, I do.
Yes. So Bayesian computation, how to sum this up. So this example is actually an example of the use of Bayes formula. So Bayes' formula is named after the Reverend Bayes, which gives his name to Bayesian Statistics.
Ah.
And his contribution was really only this, or almost only this simple formula that we use now. Whereas the idea of using this as a general way of learning something is something that has been added afterwards, but the technical part is really only summarizing what we have done. So any computation in Bayesian statistics uses the same storyline as we have used right now. Of course, technically, there are some things that are sometimes a little bit more difficult, but philosophically, the ideas are the same. So the first part is a state space is constructed, representing the possible states of the world that we consider. Then probabilities are assigned, and well, there's something here, but somehow they are assigned and they sum to 1. Then, so this is now a model of the world as it can be seen before you have considered any observations or data. Then you look at the data, and some states are not compatible with observations and they are discarded, and the remaining are the new model of the world. And then you adjust the probabilities of the remaining states and rescale them so that they sum to 1.
Ah.
This is Bayesian statistics. There's nothing more to it, except for some technical adjustment that one may or may not come back to. Okay. And of course, then predictions are made based on the resulting model that we have here. Okay, let's just summarize this. First of all philosophical implications of Bayesian statistics are contained in the creation and interpretation of the initial stochastic model, the prior, as if you want to call it. So that you use this as your model for the world, that is, or a model for as we talked about before, your model for the knowledge, your knowledge of the world. That is what gives the important philosophical implications, and the computations afterwards are only mathematics, basically. But then, of course, the question is, where do stochastic models come from? I mean, how do we construct, how do we select the state space that represents all the possible outcomes that are relevant? And not the least, how do we select the probabilities? Now, in this example we had, they were simply given somehow. How do we get them? Well, in this example that we had, there was like, how efficient is this test for the disease? This is something that you can, of course, you can learn that also by, using the test on lots of people with known disease status, or, well, there are other ways of learning this, but the point is that in order to actually learn these probabilities that that we had as input into our model, you have to have a bigger model to actually do learning from different earlier types of data. And then you are philosophically back to the question, how did you get that earlier model, or the bigger model containing more variables and more information that you use to find out, for example, that there is a 1% chance of every person to have the disease? Where does the 1% come from? Now, pretty easily you can see that you can bring this backwards and backwards, but it doesn't. It's like an infinite recursion. You don't get down to any firm ground.
No, there's no foundational at the bottom.
Yes, somehow you have to start with something.
Yeah.
You have to start with some kind of, this is a model that you don't get from anywhere.
No.
And then why is that a good model? By definition, you cannot have any argument for that, because if you had, then that argument would be learned from an even previous model.
Yes, very good.
So then we are really left with this idea: where do stochastic models come from? They are excellent ways of doing precise and scientific computations for predictions, but it's not really, Bayesian statistics is not a complete theory of learning. So any learning process will have to start with a model that is not learned, or in some sense subjective, as some people would say. So this is the philosophical problem, you could say, with Bayesian statistics, or well, you could say with any learning model, actually. My personal, just to end with the last point here, my personal idea here of where models come from is really to say that the functionality of our brains, could one argue that the functionality of our brains as formed by evolution represents an initial model? So that in practice, when we do learn as babies and then later as adults, we do it within the confines of our brains. And so the structure of our brain is sort of a type of underlying model for learning, or a starting point for how the learning process comes about. And then you actually transition from having a model for learning to needing a model for evolution. And this is my current point of view, that really what you really need to model in order to understand both learning and these philosophical questions that we are faced with is to understand evolution. Oh, but that would be a different lecture. Or, I mean, I'm not really an expert, so I can pretend to say that, but this is what I'm interested in, to understand and formulate mathematically how evolution happens. Okay, so that was what I had for a kind of a little bit, including a little bit of mathematics into our philosophical discussions on this.
Indeed. Fantastic, Petter. Thank you very much. Most instructive and interesting as well.
Mm.
And there's already some questions popping up in my head, or comments. I think the fourth thing you put there, could you put it up again? Is
Yes.
it still there? Could it be the third, fourth? Sorry, should have told you earlier. The third one.
Yes.
Any learning process will have to start with a model that is not learned or subjective. So that thing, that is the one that makes our listeners and viewers interested. It's more different than you think, actually. This has been checked within academia. I think it was in the late 90s they checked it out, and it is about 96-97% assumes that there is some sort of we start with the outer reality, so to speak. And it brings directly rules. They don't know how, but they have an intuitive sense of that, and that reality builds itself. And when you grow up, you are infused with this reality that's already constructed somehow. And it's been argued from a few sectors within the different sciences. Very few. Recently, from the science of cognition, they changed completely into something that is more similar. to what you are propounding here. Within neurology, even later on, I gave you a hint with Georgi Buzaki, who do not accept the idea of what is called the blank slate, that everything is coming from the outside. It's much older within physics, but it's not known in the public, and that's quantum physics. So if you want to make a completely mad summarizing of quantum physics, it's the third thing here. That the observer decides what reality is. That is one of the reasons when I hold my lectures about quantum mechanics, I do lectures for lay people on a very basic level, but they get absolutely shocked when I say that the observer, or the observer's knowledge, or the observer's priming, or as you say, prior, decides whether reality is a wave, and you get that as an objective result. You can see it on the screen, or you get a particle, which you also can see. And then the people just go, oh no.
Yeah.
The reactions are immense, and Bayesian is very similar to this, and it's a bit more digestible than some of the more stark implications of quantum mechanics. So,
yes, quantum mechanics is quite a bit more technically and mathematically challenging, of course.
That as well, and the founder, one of the founding fathers of quantum mechanics, Niels Bohr, he said, if you're not absolutely shocked by quantum mechanics, you haven't even begun to get a grip of what it is about. It's like an LSD trip, my old teacher. But worse, there's no escape, because that's reality. So that makes it incredibly interesting. In quantum mechanics, this prior or priming or starting point is called observer-dependent reality, where the subject is deciding what happens. And it has implication for learning. Some people have been suggesting, and this is coming up to a question here, that maybe we should make some few adjustments in the educational system for two reasons. One, getting rid of the idea that everything is coming from the outside world, which we know pacifies, makes the intellect more passive. Because you get in the mood or just reading books, and you think in the end you can just gather information, and that will be enough. So you sort of pile it, or you adjust it differently, but it's an absolutely passive process, and it can be done by not so complicated computer like the ChatGPT. I think Bayesian, could you say maybe Bayesian Statistics could put a sort of question mark into that idea that information gathering, the normal statistics, frequency statistics, would that sort of in regular life or in regular reality, as a sort of philosophical question, would you think that would be enough with frequency statistics? Or
yeah, I understand sort of that there is a connection, as you say here, and but of course it's and of course, I mean, I think that the special thing with Bayesian statistics is that it does as you say, put the focus on this your experience of the world, and not even saying that the external world needs to exist at all. It's just your perception of it that matters in the learning process, your initial perceptions and what you observe, and that is how you build your knowledge. And the existence even of the outer world is not even necessary. However, Bayesian statistics does not say that there is no such thing as an external world. Of course not. So it's also very consistent with the thing that you are, or me, for example, as an individual learning. I have some imperfect partial knowledge of the world, and I have some background ideas that come somehow from my brain, and these two together builds my knowledge, which is some kind of imperfect image of the world, which then actually might exist outside of my little bubble. And so I mean, there's not, it's not saying that the outside world does not exist, but it's just that the focus is different. But then you can also, and I think we discussed this also before, you can also change the perspective and say that I don't look at this from my bubble. I look at this from my looking at other people learning, right? And then you look at those other people, and then you look at, you presume that your own bubble is in fact the real world, and then you see how other people interact with that and learn bigger and bigger parts of it. And I think that's also necessary and fruitful way of looking at things. And then in order to understand that, you need evolution. You need to understand how does other people's learning, when you study it from the outside, how does that take place? Well, it's necessarily built not only from logic, but it's also built from how their brains work, basically. And their brains work in a way that has been formed by evolution, and those forces are the ones that we need to study. Well, in a very simplified way, but yeah. So I'm just trying to agree with you, but also to say that there is. It's not like I mean, I don't think that Bayesian statistics nor quantum mechanics should be taken to mean that the world does not exist in some sense. It should, I mean, that the world is, that some kind of objective reality does not exist. Because I think that it's still consistent with that idea that it does exist. Do you agree with that?
Well, yeah, it's 40% of the producing industry today is quantum mechanical, and obviously it exists. And my old professor said it's when the observer is in on it, it becomes even more real.
Mm.
He was a bit extreme. So if you don't take in the observer and your knowledge, it won't become completely real and, oddly enough, shared by others, which is something to put your head around. But maybe it's as you say, we are all human beings, and as being human beings, our way of life, our way of being is already sharing something. And we go more into that, you and me and other people will, in our activity, be doing things that are more objective, so to speak. Like people playing a football game, they're cooperating in the game, makes it a good match, maybe. It takes two to tango. Sorry.
Yeah.
The other leg of this question was also to the educational system. When you speak about Bayesian statistics, you all shine up and you look very interested, and so does people listening in. Do you think maybe Bayesian statistics and that way of taking in our knowledge, could you think maybe it's more conducive to creativity and such stuff?
Oh, that's a very difficult. I mean, it's kind of emotional question, and for me, I like the Bayesian statistics because it makes sense to me, and and in that way, it's. Yeah, for me at least, it's closer connected to creativity, but I'm not quite sure how to make a sort of a more general argument in that direction.
Your opinion is fine.
Sorry?
Your opinion is quite fine.
Okay. Yes. No. I honestly, I think that this transition from classical or frequentist statistics to Bayesian statistics is going on in the educational system, and I do think that it will make things more intuitive for students of all ages, and also possibly more creative, or spur more creativity. But at least that it to me at least it is more intuitive, this way of thinking, and makes more sense. And I think that this is something that is shared and also shown when this has been introduced in various courses and places around the educational system. So yes, my opinion, my personal opinion is yes.
Yeah. Wow, thank you. Great. I have some few questions. We are lagging on here, but from the listeners in. What was your, it's a rather personal question, what has been your biggest challenge in going into this for you when learning this?
Well, personally, well, my background is that I was in pure mathematics, and I didn't know any type of statistics of either kind until quite late in my education. And then for various reasons, I ended up working with some statistical stuff. And then I read some classical statistics and I couldn't make sense of it. And I thought that, well, it must be me that's stupid, because this doesn't make any sense. And I was reading and I sort of put it away, and I couldn't really, I couldn't understand it. And then later on, it has become my opinion then that certain parts of classical statistics doesn't make sense. And then of course this is what we're arguing now in this kind of battle between the two types. So that was of course a challenge, to have that belief in myself, to say that, to stand your ground and say that, well, it's I'm not wrong. It is actually something that is those those who claim to represent the tradition, they have some holes in their I mean, the way to apply. I mean, there's no holes or there's no mathematical problem with the classical statistics. It's just a problem when you apply it as a theory for learning, or for knowledge about the whole world. So maybe that was a challenge. And of course, there are all kinds of other challenges, but yeah, maybe that's one thing I could mention.
Very interesting. Also, thank you very much. It's also a rather odd question here. Do you think all numbers stem from zero or nothing?
Stem from, or
Yeah, come from or are derivable from.
well, that's a difficult question, and it's rather, it's about mathematics in general, I would think. There is a construction in logic where you construct the whole number system starting with the empty set.
Oh yes, Russell. Yeah,
Yes.
yeah.
So maybe there could be a connection there where you sort of start with building with axioms and so on, and the objects are, well, you know this, I guess. So in that sense, but personally, I don't think you should put too much emphasis on saying that, to draw any kind of emotional conclusion from this, saying that everything is nothing, or or something like that. It's more like this is a very technical construction, and it's not so useful to understand or to say that zero is a particular, as the way we use it in daily life, for example. Zero is not that important in some sense. But yeah, I don't know what more to say about this question.
That was great. Well, I think we gone over the hour here, and do you have last notes to add, Petter?
No, it's just that, well, I can say that if any of the listeners are truly interested in Bayesian statistics, you should. I mean, there are many sources online. You can go and have a look at it, and you can also find online lots of discussions about philosophical implications of the Bayesian statistics. But as I said, this is about the making of these probabilistic models of the world, and how are they made, and where do they come from, and this is a big philosophical question in terms of this thing. So there's a kind of separation between the actual Bayesian statistics, which is what I do for a living, which is much more technical and mathematical, and these philosophical questions, which I rarely have the opportunity to talk about, and I'm very happy that I got the opportunity in this small set of discussions. So thank you very much for everybody that have been listening.
Thank you very much, Petter. It's valuable beyond belief. That was great. And thank you for this nice overhead introduction that answered a couple of the questions. What are your instruments and so forth? Very good introductory first take on Bayesian, as well as on top of the philosophical questions. Quite excellent. Thank you very much, Petter.
Okay.
Thank you everyone for listening, and have an excellent day or afternoon.